Greetings everyone, my name is M.Tech IT from NIT Raipur. Currently I am in second semester and today we are going to discuss about the performance analysis of classical machine learning algorithm with quantum logistic regression for cloud resource allocation. So these are the contents are outlined for today's discussion. First we need to know what motivated us to do this work. Then we need to know about the introduction, the methodology that we applied, the results that we got, conclusion, and the future work. And after that, the references. So, what is the motivation for all this, and why to apply the quantum computing when it's not even matured? So, resource allocation is a challenging problem for cloud computing. We know that. However, the resource allocation problem is NP-hard and cannot be solved in polynomial time. Here we try to see if some non-traditional method can provide us better result, like quantum logistic regression. So that is why we tried. Now, the introduction. Resource allocation can effectively improve the social welfare and resource utilization of the resource provider or a cloud resource provider in our case, which is important for research direction in cloud computing. A single dimensional resource allocation problem has been proven to be NP-hard by Keller, Firstey, and Springer in 2004. So it cannot be solved in a polynomial time. So it is very clear that if a single dimensional resource allocation problem is NP-hard, then in multiple dimensional resource allocation problem, different types of resources where CPU, memory, storage, etc. must be considered. Thus, the multi-dimensional resource allocation problem are strongly NP. So, one-dimensional is already NP hard when you just worry about CPU utilization for say. But when you worry about CPU utilization, the memory usage, the storage running out, everything, then it becomes even more hard. The resource allocation problem can be solved by using optimal algorithms such as integer programming and dynamic programming. It can be solved by an approximate algorithm such as p-TIAS or heuristics algorithm. Because the problem of resource allocation is NP-hard, the optimal algorithms can only be used in small scale data sets. On the other hand, the approximate algorithms or the heuristics algorithm only cause the problems of low computational efficiency and low allocation accuracy compared with the optimal solution. And that is the reason, the real reason why we tried a non-traditional method for this purpose. So we have used quantum machine learning algorithm, in this case quantum logistic regression. So now we know what is the purpose. Let's move on to the methodologies. So since we are comparing the results, we have to try it with several other machine learning algorithms, the classical or the traditional ones. So we have k nearest neighbors 3, k nearest neighbor 5, k nearest neighbor 7, decision tree, Bayesian ridge, random forest, support vector machine, and ensemble, and of course the quantum logistic regression. So let's first discuss about the quantum logistic regression. So it's just like a regular regression work where a line is drawn and you have to identify where the next data point will be in class A or in class B. So, but here we are using qubits. So first we need to generate intermediate quantum gates. Then we need to generate the gradient. And when the gradient is generated, we need to convert it to the classical form so we can obtain a result. So the whole process of the entire algorithm can be shown with the help of this flowchart. So here E uh, is the precision where efficiency is shown by the n-like figure, and It's also the step factor. WO is the initial value and T0, 1, 2 is the iteration number, where capital T is the dataset and the brown rectangle represents the quantum algorithm and the light purple rectangle represents the classical iterative update algorithm. And with this, after comparing, we can get the output where the parameter meets. Next, we have the k nearest neighbor. So the KNN working can be explained on the basis of this below algorithm or below steps. So step 1, we need to select the number k for neighbors. So if you are using KNN 3, the k equals to 3. If it's KNN 5, the k equals to 5. And if it's 7, then KNN 7 will be applied. So first you need to select the number k. The more the value of k is, the more efficient it becomes. But it's also true that more the number of k becomes, the more computationally demanding the algorithm becomes. So we need to be optimized. Step 2. Calculate the Euclidean distance of k number of neighbors. As I have explained earlier, if k equals to 3, then for 3 neighbors. If k equals to 5, then for 5 neighbors. If k equals to 7, then for 7 neighbors. Now take the step 3. Take the k nearest neighbor as per the calculated Euclidean distance. Step 4. Among these k neighbors, count the number of data points in each category. Then step 5. Assign the new data points to the category for which the number of the neighbor is maximum. And with this, now we have the result and a model to study. So that was KNN. Next we use decision tree. So the working can be explained on the basis of the following steps, which I mentioned below. Step 1. Begin the tree with root node, say S, which contains the complete dataset. Step 2. Find the best attribute in the dataset using attribute selection measure or ASM. Step 3. Divide the S into subsets that contains possible values of best attributes. Step 4. Generate a decision node which contains the best attribute. And step 5, last step, recursively make a new decision tree using the subset of dataset created in step 3. Continue this process until the stage is reached where you cannot further classify the nodes and call the final node as a leaf node. And that's how the decision tree is gonna work. Next we have random forest. So random forest works in two phases. The first is to create the random forest by combining n decision tree, and second is to make prediction for each tree created in the first phase. The working process can be explained by the below steps. Step number 1. Select random k data points from the training set. Step number 2. Build a decision tree associated with the selected data points or the subsets. Step number 3. Choose the number n for decision trees that you want to build, that you want to create. Then you just need to repeat these steps from step 1 to 2, from step 1 to 2, again and again. After that, you will reach a new step, that is step 5. For new data points, find the prediction of each decision tree and assign the new data points to the category that wins the majority of the votes. And with this, we have concluded a random forest. Next we have is SVM or support vector machine. The goal of support vector machine algorithm is to create the best line or decision boundary that can segregate n-dimensional space into classes so that we can easily put new data point in the correct category in future. The best decision boundary is called hyperplane, and there can be more than one hyperplane. SVM chooses the extreme point or vectors that helps in creating the hyperplane. These extreme cases are called support vectors, and hence the algorithm is termed the support vector machine. So now that we have discussed all the algorithms that we have, not all but some that we have used, now we need to go through the results. So the results, as we validated the performance analysis between quantum logistic regression and several classical machine learning algorithms for the purpose of resource allocation, in the cloud environment. And we have chosen error function as the main parameter for the validation of results. During the time of evaluation, we clearly found out that the classical sklearn error was 3.96 into 10 to the power minus 7, whereas the quantum error was 1.08 into 10 to the power minus 4, and we can clearly see here the huge difference in these two types of error. It's clearly understandable that quantum logistic regression is not better in terms of performance when it competes with classical linear regression. For the cloud resource allocation, we must remember this point. For cloud resource allocation, there are several cases or results in which the quantum logistic regression is way better than the linear one. But here in this case, it's not. Now the second phase of results. So we have shown the classical ML models and their train and test error. So KNN3, we have 2.96 into 10 raised to the power minus 4. That is the CPU error usage in train error. Then we have KNN5 and KNN7. So as I explained earlier, the values increased, performance increased, the values decreased in the error. But it got high for KNN7. So but since it become computationally not feasible, that is why we see this huge difference in the result. Then we have decision tree and Bayesian ridge, random forest, SVM, and assemble. So in case of the train error, the minimum error is shown by decision tree. It's really good for training error in CPU usage. And if we see another column, then we have the test error. Decision tree again gives us better result than compared to any other. So that trend continues with the memory usage for testing and training. So decision tree is best for the cloud resource allocation, but it's also computationally highly demanding. So we need to apply some optimal algorithms for that. So now that we have discussed about the result, we need to go through the conclusion and future. So it is an innovative idea to use quantum logistic regression on cloud computing for the resource allocation problem. By learning the training data, the algorithm can make feasible solution very close to optimal solution in terms of social welfare, allocation, and accuracy and resource allocation. It is verified that there is need of potential model in optimal resource allocation. It presents a new solution for multidimensional cloud computing resource allocation. One of the major tasks is for future research is to find and apply more such algorithms and also increase their efficiency, as we know that it's a growing field and it will be better in future. So we need to keep on doing it again and again so that we can achieve what we wished in earlier phase. And now we have to go through the references. So these are some references that I have mentioned, since I could not mention all of those. So these little references have been mentioned. And with this, I would end this presentation here. Thank you so much.